All right, in the last video, we looked at an ellipse that had a center at the origin and had foci on the x-axis to the left and to the right, C units. And so I'm actually going to draw in here. This is C units in length. And we particularly have an ellipse that is wider than it is tall. We're going to look at other ellipses later that have more height than width, but right now we're just focused on wider ellipses. Now, we also said that there was a property of ellipses, and this property was that if we start at one of the foci and we move in a straight line to a point on the ellipse, and then another straight line to the other focus, that total distance would be 2a. And what I want to do in particular here is I want to look at the point that's at the top of the ellipse. So we know that the distance from the first focus to that point and then down to the second is 2a. And what that means is that the distance from that point to one of the foci is just a. And then lastly, we know that b squared equals a squared minus c squared. And if I draw in this line segment here, we have a right triangle with hypotenuse A and one of the legs C. And if we call this other side B, we know that this is the relationship, b squared equals a squared minus c squared, from the Pythagorean theorem. So these are actually the distances A, B, and C drawn in on the ellipse. So when we have an ellipse that satisfies an equation like this, specifically with a greater than b, there are certain properties that will always be true. First of all, the center of the ellipse will always be the origin. Next, we call the points on the ellipse that are the furthest away from the center the vertices. And these are going to be at the points plus or minus a, comma 0. So this distance actually is also a. A isn't just the hypotenuse of this triangle. A is also this distance right here. And of course the same on the other side, but I don't want to draw it there because that part's already getting a little bit crowded. So the vertices are at the points a, comma 0 and negative a, comma 0. And actually this whole distance between the vertices, we call that the major axis. And the major axis has length given by 2a. Of course, because half of it is a and the other half of it is a, we get 2a. Now, we also have what we call a minor axis. That is kind of the width in the other direction, perpendicular to the major axis. And the minor axis length is going to be 2b, because of course we can go up b and then down b, and we end up with 2b. And then the foci are going to be at the points plus or minus c, comma 0. So these are probably the most important parts of that ellipse, the things that we'll be looking at. And when I actually graph an ellipse, I look at the denominators here, a squared and b squared, to figure out what a and b are. And those actually tell us how far we're moving in each direction to get the intercepts. So here we can see that the x-intercepts are at plus or minus a, comma 0. Those are the vertices. And the y-intercepts are at 0, comma plus or minus b. So these denominators help us find the intercepts very quickly. Now I want to take a look also at a vertical ellipse, and I'm just going to sketch this by hand, so it's not going to be nearly as pretty as that computer drawn one. As you can see, definitely not as pretty, but you can see I tried to draw an ellipse. So when we have x squared over b squared plus y squared over a squared equals 1, again with a greater than b, but in this case the denominator on the y squared is larger. When this is the case, we're going to have an ellipse that's centered at the origin, but it's going to be taller than it is wide. So it's still going to have center at the origin, but in this case the vertices are going to be vertically placed instead of horizontally. So the vertices are going to be at 0, comma, plus or minus a. Those correspond to y-intercepts now, because we've got that larger coefficient underneath the y squared. And then we still have that the major axis has length 2a. It's just that the major axis is vertical now, and the minor axis has length 2b. That is unchanged. But the other thing that changes is the foci, because they are going to be above and below instead of to the left and to the right, because everything is vertical here. The foci are located at the points 0, comma, plus or minus c. So the foci are going to actually be above and below the center instead of to the left and to the right of the center. Basically, we've just taken this ellipse and we've rotated everything 90 degrees so that it's taller instead of wider. Now that we have both of these, I want to do one quick problem where we're just going to sketch a graph of an ellipse so that we can get practice with one with real numbers. So let's sketch a graph of x squared over 25 plus y squared over 16 equals 1. We recognize that this is the format for the equation of an ellipse, and because the denominator of x is larger than y, we know that we're in this situation where it's going to be a wider ellipse. So we know that the center will be the origin. The vertices are going to be to the left and to the right at plus or minus a, comma, 0. Now, if a squared is 25, that means that a is going to be positive or negative 5. So those are going to be the x-intercepts. And then for the y-intercepts, we look and we see that b squared is equal to 16. So that means that b is going to be positive or negative 4. So those give us the y-intercepts, and so we can use those to draw our ellipse. And we weren't asked for the foci, but let's actually find the foci. We know that the foci satisfy b squared equals a squared minus c squared. B squared is 16, a squared is 25. So here, if we subtract 25 from both sides to get that c term alone, we get negative 9 equals the opposite of c squared. If we take the opposites of those, multiply or divide by negative 1, makes them positive, c squared equals 9, and then of course c equals 3. And so what that means is that the vertices are to the right or to the left 3 units at the points 3, 0, and negative 3, 0. So this is how we can quickly and fairly easily sketch a graph of an ellipse. But we will look at several more examples in the linked problems below. So definitely check those out to get more practice with all types of ellipses.